Okay, so in this module, we're going to take a look at polynomials or graphing polynomials. In the last module, we just introduced the polynomial as a function, starting off with a quadratic and then just building up in general to polynomials of degree n, right? And again, a reminder here that polynomial takes on this form, right, where n is an element of our whole numbers, right, etc. Okay, and R for I less than or equal to n, greater than or equal to 0, right? I can be any real number, right? The coefficient, right? So these, or excuse me, I shouldn't say I, a sub I, right? That is, the coefficient could be any real number, right? But the exponents, we're strictly looking at ones that are whole numbers, right? Where the highest whole number, right, the highest exponent was called the degree. In the previous chapter, we looked at various properties that these polynomials had. In this, or in previous module. In this module, we're going to take a look at their graphs. Right? Now, the first step is to just recognize a graph of a polynomial. And then we'll, at the end, or we'll build towards being able to graph, to give a, we'll say like a sketch of a, excuse me, of a polynomial graph. All right. Now, the nice thing about these polynomials is that their graphs are always going to be, graphs are smooth and continuous. Okay, so let's look at a couple of examples here of possible polynomial graphs. Now, we hinted at the last module the shape of these, right? And depended on what the degree of these, right, they had a general shape where, right, if it had like an odd degree, it looks something like this, right? And then a even degree, it looks something like this. Right now, had they, excuse me, they exhibited the same end behavior, right? Where, and if it went off, in this case, infinity, negative infinity, depending on what the coefficient was, these could be kind of flipped across, reflected across the x-axis. The same thing here, depending on what the coefficient, the leading coefficient was, these could be reflected across the x-axis as well, right? But in this case, right, it went off to the same infinity, in this case positive, right? But sometimes negative if the leading coefficient was a negative number. I'll label my axes here. And in certain instances, and we'll look at when those instances occur, there might be some more interesting behavior in the local sense, right? Local being, right? Well, I'll use the word near the origin. Okay. So these will be examples on what that behavior might look like is something that looks like this. So maybe it looks like this, right? Some more interesting behavior here in the local sense, right? Where it crosses the x-axis and it has these behavior here. Okay, all right, and here, right, different turning points, x-intercepts, y-intercept, etc. We'll go over how to calculate these the intercepts as well in this module here. Right, so by smooth, kind of has, you see this smooth, continuous, we can draw the graph without having to pick up our pen or pencil. Right? Now, one thing that we notice here of all of these graphs, the three that I have in front here is, and this will hold for any polynomial, right, that the domain for any polynomial is all real numbers, regardless of the polynomial. Now, the range is a different thing here, right? Because if we notice here, the range are the y values. If we notice here, there's a certain point here where there's no values below this value, right? So that has a different range than this value here, where we see that it looks like, and it does attain every single y value. Right? And the same thing here, there is a point here where there's no value above it, right? This point is the highest point here, everything else is below it. Okay, so just keep that in mind. Domain, always constant though, for any polynomial, right? Memorize that fact, domain, all real numbers, all the time. Okay, and it has these kind of smooth kind of curves, right? As opposed to one example is the absolute value, which is not a polynomial, and we could see here, right? While it is continuous, it is not smooth, right? A polynomial, or excuse me, an absolute has this sharp corner there. Okay, so that one is not smooth here. Okay, so our polynomials have these nice smooth lines here, always continuous. All right, now the first kind of building block here in getting us to draw a graph is to find the x and the y intercepts. All right, so here, finding x and y, finding x and y intercepts. Okay. All right, so let's start off with this example here. So for this example, let's say we have the function c of y equals to 3. So y plus 2, y minus 3, y plus 5. Okay, oh, excuse me. Yeah, c of y, okay. All right, so it's a function in terms of y. All right, okay, so here to find, let me, sorry, I don't like that. My apologies here, let's use just our regular notation here. It'll get confusing here. It's c of x. Not sure why I wrote it down like this, but c of x plus 2, x minus 3, x plus 5. All right. Okay, much better here, right? So you have a function where the independent, as always, is our x variable. The dependent is y. Okay. All right. So here, it's in the nice factored form already, which I like, right? It makes things easier to identify. There's not much initial work needs to be done. We can jump right away to finding the x and y intercepts. All right. Now let's do the y one. That one's a little more straightforward. Y-intercept, and again that means x is 0. So we just plug in 0 here for x. So c of 0 would be 3 times 2 times negative 3 times 5. Right. So what do we have here? So let's see, 5, 10, negative 9. So we get negative 90. All right, so that'll be our y-intercept, right? The y-intercept being negative 90, 0. Okay. All right. And then here, the x-intercept, that means y is 0, or in other words, here this function I set equal to 0. Okay. Now, since it's in its nice factored form already, right? So we have 4 factors here. 3, x plus 2, x minus 3, x plus 5. Right now I have 4 factors getting multiplied together, and the result of that multiplication is 0. Now, we have this nice property, because it's equal to 0, what has to be true, right? There's no other way that this can happen unless one of these values is 0. Right, now 3 can't be 0, so that's not going to factor here. But x is my unknown, so either one of these 3 needs to be 0. Right, so x plus 2 needs to be 0, or x minus 3 needs to be 0, or x plus 5 needs to be 0. Okay, so now we have 3 linear factors that we can solve for rather easily. X equals negative 2, x equals 3, x equals negative 5. All right, so we have 3 zeros, which makes sense. This polynomial is of degree 3. All right, if I think of x squared, x cubed, right, all of the leading terms. Now, there's a bunch of other factors in there, but I'm not worried about finding those. I just am pointing out and identifying the degree of this polynomial. All right, so that works all great if it's given to me in its factored form. Right, but what if it isn't? In that case, we do have to do a little bit of work, right? So let's do an example where that happens to be the case. Right, so for this example, let's say we had f of x equals to x to the 6th minus 3 x to the 4th minus 4 x squared. Okay, so we have a polynomial of degree 6. So we have a possibility of 6 x intercepts. Again, possibility, not guaranteed, just a possibility. At most 6. Okay. Alrighty then. So again, the goal here is find x and y intercepts. All right, let's do the easy one here. The y-intercept, x equal to 0. All right, so f of 0. Oh, all of these get plugged in a factor of 0, so that goes to 0. All right, so my x-intercept is the origin, which also happens to be my a x-intercept as well, right? Because x is 0 there as well, right? And that will show up in the second part here, but just keep that in mind. We actually already found one x-intercept as well, right? That one came in for free. Okay, x-intercept, right? In this case, y equals 0. So x to the 6th minus 3x to the 4th minus 4x squared equals to 0. Okay, so it's not a quadratic. Can't use the quadratic formula. Right, so from here, whenever we're left with something like this, the next step is let's try and factor it. I notice right away I can factor out an x squared. Right, they all have an x squared in common. Right, I always choose the smallest exponent to factor out. So we get x squared, so we're left with x to the 4th minus 3x squared minus 4, right? That doesn't become 0, it's a factor of 1, right? 4 times 1 is 4, set equal to 0. Okay, now I'm not quite done here. Right? Turns out I can still, this is already in a factored form. Not much I can do here. Now I can factor this similar to how I do factoring a quadratic, right? Now this is not a quadratic, but it does have the quadratic form, or if you recall, the quadratic form is usually an x squared, x constant. Well, this is x to the 4th, and 2 happens to be half of 4. So if I have that same pattern where we have an exponent, half the exponent, then a constant, I can apply the same type of techniques of factoring that I do these trinomials, these quadratic trinomials. Right? So I'll split this up in half, x squared, x squared. Now I'm looking for values that multiply to negative 4, but add up to a negative 3. And that can be possible splitting it up this way, right? Negative 4 times 1 is a negative 4. Add negative 4 plus 1, negative 3. All right, and that works out, right? X squared times x squared, x to the 4th. The middle term, 1x squared minus 4x squared, negative 3x squared. And that last term, negative 4. All right, and actually I'm not done factoring either, right? This is a difference of squares. This is in its factored form already, not a difference of squares. That's plus, right? So there's no sum of squares that we can factor. So we just leave it like that. Okay, so now I have 1, 2, 3, 4 factors here, and they're equal to 0. And again, from here, set each one of those equal to 0. All right, so here x takes square root, x is equal to 0. Again, usually plus minus, but since it's 0, right, plus minus 0 is just 0, one number. And again, right, we knew that already from finding the y-intercept, but here it is again. All right, minus 2, x equals to negative 2. X equals to 2. And then here we have x squared equals to negative 1. We have a complex number, right, or imaginary number. Right, bit of a misnomer. They're very much not imaginary, right? They are actual numbers. But since we are dealing with the real plane when graphing, we ignore those for our graph. Okay, so it's not a real solution, a real number solution. So we leave that off, not part of our solution here. So we have 3x intercepts, right? We got to intercept that 0, 0, negative 2, 0, and 2, 0. Okay, so that's how you find the x and y intercepts.